Well, welcome back to our DC electronics topic series. Today's topic will be topic number 8. We'll be discussing troubleshooting series parallel circuits in electronics technology. And this series of videos is intended for either home use or to supplement what it is that you're learning in an electronics engineering or electronics technology class in college. This for advanced high school students can also be applicable for either home study or in conjunction with, say, part of your physics class or electronics class if you happen to have a dedicated course of such in your high school. The topic we will go ahead and launch right now. And let's go ahead here. And let's go ahead and define what are series parallel circuits. So in previous videos, we talked about series circuits. We talked about separate topic of parallel circuits. Now we're going to combine these. And so what it is that you have here is where part of the circuit contains devices that are in parallel with each other, and parallel components, they split current, they divide current. And then other parts of the circuit are series components, meaning they don't split the current. They have only one current path that is consistent with the current that goes to the voltage source or coming back to the voltage source. So if we take a look at the illustration that you have, the schematic illustration that you have, is we have an R1. We have an R1 that is in series. It's in series because it's a single current path, in this case, out of the voltage source. And then we have an R2 and an R3 that are in parallel with each other. They do divide and split the current, so to speak. And what I'm going to try to do with these schematics is give you something outside of what you're likely to see in the textbook, just to challenge you a little so that the drawings are not the same textbook drawings that you're likely to see in class. But the principles are the same. So if you take a look at the circuit build that I have, the circuit build that I have on the right of the diagram corresponds with the schematic. I have a R1 that's 220 ohms in the upper left. It is such on the schematic. It is also such on the breadboard. There is a point B that is, excuse me, a point A that is on the left side of R1 in both the schematic and the circuit build. The other side, the right-hand side of R1, I've designated as point B, and I've designated it on the schematic as well as on the board. Now, the voltage source is not shown in the traditional textbook on the far left-hand side with the positive plate on top and the negative plate on the bottom. I decided to do something a little bit different to challenge the more advanced, the eager jackrabbits of the bunch and show you something different. But the principles, again, are the same wherever I put the voltage source. And in this particular case, I've placed a voltage source at the top of the circuit, and I have the negative plate attached to point B in the schematic. And if you take a look at the circuit build, do I have point B attached to the blue rail? Is it attached to the negative side of my power rails? The answer is yes. The other side of my voltage source, which is the positive plate in my schematic, is attached to point C. Look at my circuit build. Is my positive rail marked with a little plus sign from the red rail, is it in fact attached to point C, the top of R2? Take a look at the schematic. Take a look at point C and point D on the schematic. Are they joined together? Is there any component between them other than a wire? And on the circuit build, you can see point C and point D are connected with each other with a orange jumper wire. There's no device other than a wire between them, meaning there's no LED, there's no resistor, just a wire. So we'll use this phrase a lot and just share this with you now that point C and point D are electrically the same. I said that you would hear that phrase, electrically the same. Now you should repeat, say electrically the same. Specifically, point C and point D are electrically the same. Then the other side of R2 and R3, remember, we said in a previous training video, the parallel circuits training video, we said that devices are in parallel with each other if and only if two conditions exist. Do the upper leads meet at a common point? Yes, the upper lead of R3 and R2, they meet at point CD, which is electrically the same point. They meet together. And then in order to satisfy the definition of parallel, do the lower leads, the leads on the other side of R2 and 3, do they meet? And yes, they do. They happen to meet at point E and F. And point E and F, as we've said before, if they're connected with only a wire between them, point E and F are electrically the same. Do I have that connection on the breadboard? And you'll follow this. It's a little, I've got jumper wires in here at the bottom of R2 and jumper wire at the bottom of R3, and they're a little staggered in terms of row H and row I. And the purpose of these little green jumpers is they will provide an excellent point for measuring currents. I can measure current of I2 separate of I3 by just simply lifting a jumper wire. But the bottom line is are the bottom leads of R2 and R3, are they ultimately connected to the same point, meaning the yellow jumper wire? Okay, the yellow jumper wire between E and F. Connect the bottom of the resistors together as you follow the wires of the bottom of the resistors. Then finally, another point of interest is where I've placed ground symbol. The ground symbol is placed attached to point E. In previous illustrations and in a lot of textbook illustrations for beginner electronics students, the ground is usually placed on the negative plate of your voltage source. Again, I wanted to show you something a little different, a little more challenging. And if you recall, what is ground? This is not earth ground in the electrical world. In the what you would find electricians would be associated with. Ground is a little different in your household wiring. The ground in schematics and electronics technology is simply, and write this down, ground is a common reference point. I repeat, listen carefully. Ground is a common reference point. Ground is 0 volts. I repeat, ground is 0 volts. And so ground does not have to be attached to either plate of the voltage source. It doesn't have to be attached to the positive side nor the negative side. It can be placed anywhere as a point of interest. And you'll see why it's going to be interesting as we go through the circuit analysis in the pages to come. So series parallel are defined as part of the circuit is in series. R1 is in series with the voltage source, and part of the circuit is in parallel. R2 and R3 are in parallel with each other. The schematic build shows the voltage source in an untraditional location, but like I said, the analysis principles are identical to what it is that you'll find in a basic textbook on a basic series parallel circuit. And then the circuit build is reflective of all of the points of interest to the schematic. So let's go on to see what it is we are tasked to do. All right. Your troubleshooting of series parallel will entail calculating these quantities. Now, some of these you already know how to do. Some of these I'm going to have to explain to you how to do, but this is our target page. You're not going to be able to do this right now without some coaching from myself. But you'll be able to learn how to do all of the calculations outside of Ohm's law in a very, very short period of time. So we will fill this page in with your calculations and show you how to get those calculations. And once we fill this page in, then we're going to do some measurements to verify that our calculations are spot on. So as before, what it is I've recommended is you should be journaling into your journal the very important points of interest, points of consideration, certainly formulas that we will be discussing. You should be putting those in your journal and just mark today's journal, whatever today's date is, and the topic is topic number 8. We are going to play with series parallel circuits. So we'll come back to this page in various parts along the way. So let's go ahead and start with the first part of interest, and that is here. First thing you want to do when you're confronted with a series parallel circuit, take a look at the task. I've outlined the tasks in black. And the task says, the first thing you got to do is simplify the circuit to a single total resistance. RT stands for resistance total, total resistance. Okay. So what you should write down in your notes for series parallel task is to simplify the circuit to a single RT. So how do we do that? Well, how we do that, if you take a look at the original circuit that's on the upper right, it shows R1 in series with the voltage source, and it shows R2 and 3 in parallel with each other. So how do I begin simplifying this? There is a method, and that method begins with step number 1. Step number 1 says you're going to combine all parallel resistors to an equivalent single resistor. Okay. Now, previously we calculated RT, our total for parallel circuits, but our total for this circuit is different than the R total for the parallel portion of the circuit. So take a look at what I've got here. I've written REQ. Now, EQ stands for what? What do you think? Think. It's right there, right above REQ. It's an abbreviation for equivalent. It is the total resistance of the pair of resistors that are in parallel with each other. It is not the R total of the entire circuit. So for the pair of resistors that are in parallel with each other, so I'm showing REQ equals, in parentheses, R2 parallel with R3, and I'm using double slashes to show the parallel relationship between R2 and R3. Now, you already know how to calculate that parallel relationship. If you refer back to the parallel video that I've set up before, you'll be shown what we call the reciprocal resistance formula. The takeaway with the equivalent resistance is that it must always be calculated to be less than the lowest ohmic branch. Since I only have two resistors, R2 and R3, in parallel with each other, which of the two resistors is the lowest branch? You have 330 on one branch, you have 100 ohms on the other branch. Guess what? Your total for that pair of resistors is called REQ, for R equivalent, and it must be less than 100 ohms. If you calculate anything more than 100 ohms, go back to review your calculator basics that I've shown in the previous video. Now, once you calculate that value, for step 2, then you must redraw. And this is really important. As you're taking down notes, you must show the original schematic, and then you must show the redraw. So the redraw simplifies from the 3 resistors to a transition circuit that's a simple series circuit, a transition circuit that shows 2 resistors. So how do we go from 3 resistors to 2 resistors? What we've done is we've combined R2 parallel with R3 to become a single equivalent resistance. You calculate what that value is. It's something less than 100 ohms. Where does that equivalent resistance exist in the circuit? It still is on the far right-hand side. So instead of a pair of parallel resistors of R2 parallel with R3, they have been combined into a single, what phrase did I use? You should be speaking out loud, equivalent. R2 parallel with R3 have been combined to a single equivalent resistance called REQ. And so you draw a transition simple series circuit, because you're taking the series parallel, combining the parallel components into becoming a transition simple series circuit. And we call it a transition because depending upon the number of devices in your schematics, you may have more than one transition. You might have 2, 3 transitions before you get to the final drawing. All right, that's step 2. Take a look at step 3. Step 3 says, then what you're going to do is combine all the remaining series resistors into a single total resistance. So if you look at your schematic, your transition schematic on the lower left, you now have a simple series circuit. There's only the original R1 in series with the new R equivalent. So what do you do to find total resistance in a series circuit? You just add them. So you take a look at my formula. RT is equal to the sum of R1 plus the 2 and 3 in parallel with each other, or stated more simply, RT is equal to R1 plus REQ, because I only have two components I'm adding together. Then what you do in step 4 is one more redraw. And this redraw is critical because we need these redraws when we go to solve the circuit for other considerations. When we go to solve the circuit for currents, when we go to solve the circuit for voltages, we need these redraws in your journal. So it says in step number 4, you're going to redraw to simplify the circuit to a final simplest series circuit with a single R total. And if you look at the schematic on the lower right, there's only one voltage source and one resistance, and that resistance is your total resistance. Now, notice I don't have any numbers here because we're going to be doing these calculations together. So what you ought to do right now is put the video on pause and do these calculations. When you put it on pause, this frame that I have on the screen will remain. And what it is you want to do is to do the calculations. You do the calculations. There's only 3 calculations for you to do here. 2, actually, 2 calculations for you to do. And you write the calculated values where? In your journal. Okay, so listen carefully. You need to do the calculation. You need to write it down. Don't just go to the next slide and say, oh, I'll just read it. I won't calculate it. Sorry. That's not how you're going to build a solid foundation in electronics technology, electronics engineering. It's not going to happen just by glancing and looking and saying, oh, okay, la-di-da. No, you need to do the hands-on approach and do the calculations. And let's go ahead, and I will also put this on pause, and we'll do this together. All right? Now let's go ahead. All right, so if you look at the camera screen, what it is that you're going to see is the step number 1 says to combine all parallel resistors into an equivalent single resistance. So REQ is equal to R2 parallel with R3. So let's go ahead and review what R2 and R3 are so we can do that parallel calculation. We can see that we have 330 parallel with 100. All right, so with our calculators, what we've done previously is, let's go ahead, light the puppy up, and we should have 330. Since we're not using any engineering here, let me use this one here. It's a little brighter, maybe a little easier to see. And we'll go 330, okay? And we will hit our reciprocal key, which is the 1 negative, see, X negative 1. So our display shows 300 negative 1. And then we will hit the plus, and we will have 100. And 100, we will then reciprocate that, reciprocal, and then hit equals, then hit equals, and hit the reciprocal key one more time, and then hit equals. And lo and behold, because this particular calculator doesn't shift into engineering prefixes, we just simply, and we know that this is not engineering notation because this is a 10 power something other than a multiple of 3. So this is scientific notation. We need engineering notation. So we're going to hit the engineering button, ENG, voila. So what it is that you have is 76.74 ohms. That's what it is you should be able to calculate on your calculator, and you should write that value down. So you should have done R2, which is 330 reciprocal, plus 100 reciprocal equals 100 reciprocal, okay? All right, and so write that value down. And what it is that you have now is the R equivalent. We've just calculated the R equivalent of these two parallel with each other. So this particular position should be filled with your 76.74 ohms. Then you redraw the circuit. And as you redraw the circuit, what it is that you should see is 2 components in series with each other, because this is a transition circuit that you should have redrawn into your journal. And so the REQ, this value now, instead of it being a question mark, is 76.74 ohms. You see that this is in series with R1. So how do we find R total in a series circuit? In a series circuit, R total is the sum of the series components. So it would be 220 plus the 76.74. And so we'll just go ahead and do that. Just simply hit add 220. And again, scientific notation, we're going to hit engineering. And engineering, we should see 296.74 ohms. Okay, so 296.74 is what you should get. And that's what you should write down for our total. And our total is written over here under step number 3. You're going to find the 220 plus REQ of 76.74, and that calculates to be the 296 to 96.74 ohms. So that's what it is you should calculate for our total. Okay, so this is just a quick review of how to do the parallel calculation. So from this slide page, you've just finished the calculation. You've written the values down in your journal. And let's go ahead and do our check screen. And right here, yes, you should have a calculation for R equivalent of 76.74 ohms. Add that to the 220 that is in series with the 76.74 ohms and the schematic that's shown on the lower left. And you should have a total ohms in the schematic on the lower right, single resistor, single voltage source showing 296.74 ohms. All right, so now that you have the calculation, how do we know if the circuit build matches our calculations? So with that being said, let's go ahead and put this on pause and let's go back to the camera and let's do some ohmic measurements. All right, my friends. So if you recall, when we do any kind of measurements with your digital multimeter, first thing we do is take it from the off position to diode test or continuity test, which is this one here with the sound symbol. Light up the display since this does light up nicely, and you can see that yes, we do have the sound symbol here, and it does show that we're ready for a continuity test because you want to make sure your probes are working properly before we go to apply our probes to any of the circuits to be measured. So on this particular instance, I'll touch the two probes together. On this multimeter, there's a beep, which may or may not be picked up by my microphone, but you will see that this will be a good test showing pretty near down to 0 ohms. The display will change from out of limit to 0 ohms, and there for this multimeter, this will also light up with an LED here. So here we go, touch the two leads together. I have a beep. It goes down to 0 ohms and the LED lights up. Touch again. All right, now this is ready. I will now go to ohms. And before I go to put this on my circuit, one of the things that you have to remember was you cannot have the power supply powered, nor can you have the power supply on the board. So we will go ahead and remove the power supply. There we go. And the schematic can be tested for total ohms where I had the voltage source connected, and the voltage source was connected at the plus terminal and the minus terminal of the circuit. And you noted, you hopefully recall, for measuring resistance, it doesn't make any difference at all which probe goes where, because resistors themselves, resistances, are not polarized. Currents and voltages are. So we expect to see something close to 296.74 ohms, and I'm going to touch, for the fun of it, red probe there, black probe there. Let me actually touch the metal. Hopefully we'll get something close to 296, and I get 297.9. Okay, pretty darn close. That means my R1 of 220 ohms, which I should have measured before putting on the board, is in fact correct. My R2, which is 330 ohms, which I should have measured before putting on the board, is also correct. And my R3, which is 100 ohms, and again, I should have measured that before coming on the board, is also correct. And not only are the ohms correct, they are also correct in their respective positions, such that given the schematic and given the circuit build that I've built to match the schematic, yes, these ohms match. So I will go ahead and touch here and touch here. And there's my 297.9, which is within the tolerance, considering we calculated 296.74. Now, that's RT. How about our equivalent? Our equivalent is only these two guys in parallel with each other. It cannot, if I want to measure these guys parallel with each other without any type of influence of that R1, all I need to do in this schematic is just simply remove a jumper, and the easiest jumper for me to remove is this brown one way over here. So I'm just going to scoosh it up, set it aside for a moment. And now if I go to measure my R2 parallel with R3, I put one probe above, one probe down below. I hopefully get 76.74, something close to that. And lo and behold, I get a little bit more, which is okay. I'm within the ballpark. So 76.74 ohms was my target, and I'm measuring 77.3. If I'm measuring 100 something or 200 something, then I definitely have an incorrect circuit build. All right. All right. So my individual ohms are correct. My parallel ohms are correct. My total ohms are correct. I need to rebuild the circuit. So I cannot forget that I've yanked the jumper out, put the jumper back, and just double check with our total one more time to make sure that that rebuild was correct. So touch metal and touch metal, and hopefully we get back our 297 and change, which we do. Okay, my target was 296.74, and I'm not that far away from it. All right, that's great. So we did the calculations for our equivalent. We did the calculations for our total. We have now done the measurements for our equivalent and the measurements for our total. We can move on to the next step. Okay, my friends, if you find that this approach of showing you the theory based on a schematic, showing you the built circuit on the breadboard in the neat build fashion, as I've shown you before, and then doing the calculations and then verifying the calculations with measurements. If you appreciate and like this approach, then definitely just give the video a like, a thumbs up, and subscribe. And as new videos are created, you'll be informed of the new set of videos as they come out. So that's certainly the metrics with YouTube, with the likes and the subscriptions, really do help me be able to generate these and make them as accessible to you as quickly as possible. So without further ado, we'll go on to the next step. We've taken everything here. We've simplified the 3 resistor circuit down to 2 resistor circuit down to 1 RT. So the next step is something called current analysis. So yes, that's another phrase you should be writing down in your journal. This is very, very important topic and really will help you noodle your way through any of a number of complex circuits forthcoming. So current analysis is introduced to you here. And what it is, the task is called current analysis. And if you notice the drawings, I have the drawings. Upper left will be the first one, lower left will be the second one, and in the upper right will be the original, which will be the third drawing that we will analyze. So when we do current analysis, we'll start with the final simplest series circuit that we had previously. Remember, we did a simplification, we did redraws of simplified circuits down from 3 resistors to 2 resistors to 1. Current analysis works in reverse. Current analysis allows us to take the simplest circuit and analyze it nuts and bolts to everything we want to understand about that simple circuit, and then apply that information to the transition circuit, and then apply that information that we learned in the transition circuit back to the original circuit. And we'll ultimately be able to noodle out these currents pretty quickly, okay? So very first, step one says start with the final simplest series circuit that had the RT, and your task is to calculate IT. Now, how do we do that? Ohm's law. You remember Ohm's law? From Ohm's law, you wanted to take voltage divided by resistance to calculate current. So I total, according to this formula, is equal to V total divided by R total. So what do? You take the 5 and divide by R total, and R total was 296.74 ohms. You do that calculation based on the numbers that you have calculated and also written down in your journal and also measured, all right? And so take 5 right now and divide by 296.74 ohms, and you will calculate a current. Write that value down. Don't just wait for me to do the work for you and you just copy the work. No, no, no. You learn best by you doing the work, hands-on. After you calculate that current, the I total, step number 2, I want you to realize here that the I total in the circuit above, the upper left schematic, is the same I total in the transition circuit you drew earlier. This is in the lower left. It's the same I total in the transition circuit, because what is the same in a series circuit? Current is the same in all parts of a series circuit. So as the upper left diagram is the simplest series circuit with only a single resistor, if we expand that back to the transition schematic of 2 resistances, where R total is now shown as an R1 of 220 ohms and an equivalent resistance of 76.74 ohms, we can show them separated. It's still a series circuit. So what does that tell you? That tells you that the current through R1, one of the original circuit resistors, the current through one of the original circuit resistors, in this case R1, is the same current as total. Think about that. R1's current is the same as total current. And hopefully you have calculated some number there and write in that number what you think R1's current ought to be. Yes, you guessed correctly. R1's current should be identical to the current you calculated for I total. All right. We'll do that calculation in a moment. I want you to look at the process first, look at the formulas we're going to play with, then we're going to do the calculations, and then we're going to verify with some measurements. All right. So step number 3, you're going to use CDF. Oh my gosh, what is CDF? Well, again, back to a previous video, look for parallel circuits video. CDF stands for current divider formula. And it's a handy formula for you to very quickly determine currents that are split between branches of a parallel relationship. So what this allows you to see is you can use CDF, current divider formula, and see how I total is split between the R2 branch and the R3 branch. Total current, whatever you've calculated in step 2, will be split between these 2 branches. Part of the current, not all, part of the current will go through R2, and part of the current will go through R3. So how do we do this? If you recall the current divider formula, again in your journal, it doesn't hurt to rewrite it again in your journal. It's okay to have a formula repeated in a number of places in your journal. Handy, because the mere act of writing it down and reading it and speaking it out to yourself is called kinesthetic learning. That is learning hands-on. So IX stands for the current through some unknown branch. That is equal to the total. This is not our total for the circuit now. This is our total only for the components that are in parallel. The R total in this case, the RT in this case, should be REQ, the equivalent of the 2 parallel resistances. Divide by that particular branch's resistance times total current. So I made a note. It says in the note, replace RT of the current divider formula with REQ. Remember, RT is solely reserved for total resistance of the entire circuit. However, REQ is the total ohms of those devices that are in parallel, and only those devices that are in parallel. So let's look at the formulas you're going to use. The current through R2 is called IR2. These are the formulas in the lower right. IR2 is equal to the equivalent resistance of 76.74 ohms, divide by the value of R2, which in this case is 330 ohms. So 76.74 divided by 330, then multiply that by your total current. I'm not going to give you that number now. You should have calculated it earlier, but pop in that number you calculated for total current and see if you can generate a value for IR2. Doing the same approach for the current divider formula for the third resistor, IR3, current through resistor number 3, is equal to REQ divided by R3. So in this case, your IR3 is equal to, yes, you're right, 76.74 ohms, divide by 100 ohms, because R3 is 100 ohms, then multiply by the total current. And then you'll get the specific amount of current only through R3. And if you've done this correctly, you should remember from your parallel circuits video that if you summate these two currents, the branch current through R2 and the branch current through R3, they should sum back to the total, okay? Because a parallel circuit divides current. Should it divide it equally? No, it should be divided depending upon how many ohms exist in each branch. We'll review that in greater detail in a moment. So right now, what I'd like for us to do is to do these calculations. So I'm going to put us on pause and go back to the camera, okay? And let's do this together. All right, so step number 1, you want to start with the simplest series circuit redraw that you've done, which is a single 5-volt source and your RT. We did calculate your RT as 296.74 ohms. So your I total should be VT divided by RT of the 5 volts divided by the 296.74. And let's see what that calculates to be. Let's go ahead and do that here and turn this guy on, and we will have 5 divided by 296.74 and hit equals. And the calculator shows you beautifully the appropriate engineering prefix. This is 16.85. Remember, you round off third digit to the second digit. 16.85 milliamps is what it is that you should be calculating. And on the other calculator, if you have the other style, method is again the same. You take 5, divide by 296.74, right there, hit equals. You get scientific notation, you hit engineering, you get metric notation. However, this doesn't show you the prefix. So you do need to convert the 10⁻³ to become milli as shown in your prefix calculator. So if you're using a non-prefix calculator, you'll need to do the conversion. And hopefully from one of our previous videos, you have entered into your journals the engineering prefix chart by my associate professor, Nabil Al-Hamal. And this has been very, very handy for a number of our students. Okay, so that's from previous video. Anyway, so 16.85 milliamps is what it is you should have for I total. Now, the next step is for us to take that total current, and we see that the total current is the same as the current through R1. That is here should be 16.85 milliamps. So that's what it is you should have here. Now, the next part here, we're going to do together, and that is use current divider formula. And with current divider formula, in order for us to calculate each branch, instead of R total, we're going to use R equivalent. And so it says here, we will replace R total of the current divider formula with R equivalent, because that is the total of the two values of resistors in parallel with each other. So the current through IR2 is R equivalent over R2 times total current. All right, so what it is that we'll do on our calculators is here, and we will have REQ, which is 76.74, and we're going to divide that by the value of R2, which in this case is 330. And then we're going to multiply that by the 16.85 milli, and milli is a prefix button. 80, did I hit 85? 16.85. There we go. 16.85 milli. Milli is a button that is subscript right above 5. So I use my shift button. I hit shift, and then I hit the 5 button, which has the milli. And see, milli does appear. And so now when I hit equals, it should calculate to be the appropriate engineering prefix, 3.92 milliamps. So this would round off to 3.92 milliamps. And you should write that value down in your journal, in your notes for the current through the second branch. How do we do the current through the IR3, through the R3 resistor? That's shown here. IR3 is equal to R equivalent divided by R3 times total. So this should be your 76.74 divided by what? 100, and then multiply by what? Your 16.85 milliamps. Let's go ahead and do that. Clear? And we will go ahead and take 76.74, and we're going to divide this by 100 right there, and then multiply this by 16.85, shift milli, and we calculate 12.93 milliamps. 12.93, and to show you milli right there. On the other calculator, some of you may not have made the transition yet. Pardon me. We will go ahead, take the 76.74, divide by 100, and multiply by 16.85. And the way I key milli into this calculator, I use my 10x key. 10x, negative 3, and then hit equals, hit engineering. There's my 12.93 milli. All right, you hopefully have filled in these blanks appropriately, done the calculations yourself, and then write down the value of your calculations into your journal. And now let's see what the answer sheet looks like with the values filled in. I total 16.85 milliamps. IR1 is the same as I total, as 16.85 milliamps. Using current divider formula, the formula is shown here, the math is shown here, 76.74 divided by 330 times 16.85 milliamps, I get 3.92 milliamps, and then my IR3, I get 12.93 milliamps. Does this current IR2 add with this current IR3 back up to the total of 16.85 milliamps? Lo and behold, hallelujah, yes it does. So the current divider did split the current, did split the 16.85 milliamps. It didn't split it equally. Why did it not split it in half? What do you think? This is a thought question. Now, a number of you probably already guessed it. They're not going to split evenly. They're not going to split into two equal parts, not going to split the 16.85 milliamps in half. Why? Because the ohms of each branch are different. R2 has more current or more resistance than R3. R3 has less resistance. And what it is you should remember from your parallel circuits video is in a parallel relationship, this bank of two resistors, which branch will have the greater current? That was the question. Listen carefully. Which of these two branches, R2 or R3, will have the greater current? What do you remember from the parallel circuits video? The lower ohms will have the higher branch. In other words, less resistance will allow more current to flow. It's like that garden hose. It's like a big garden hose, a 1-inch diameter garden hose has very little resistance. It flows a lot of current. But if you change over to a smaller diameter, more resistance, let's say you change to a 1/2-inch hose, it has more resistance. More resistance, which is what's evidenced in the R2 branch, is going to be less current. So do we have, in fact, IR2 as less current? Do we have for IR3, in fact, more current? So it's nice to have that reviewed for us. Now let's go ahead to the next task. Next task, let's go ahead and review these concepts. It's very important to take a moment and review this, and it's very handy if you write down the review concepts, because this is a pause for us to do a check, mental check, to see if our understanding of electronics is at the same foundation level. So it says we're tasked with series concept review. What is the most important concept about a series circuit? I have this in yellow. Current is the same in all parts of a series circuit. What's the same? Current is the same in all parts of a series circuit. So that 16.85 milliamps for the total is the same as the current flowing through the transition schematic, so that therefore IR1, the current through R1, is the same as I total of 16.85 milliamps. Next, task for parallel concept review, we said that parallel circuits divide current. Okay, there's other characteristics of parallel circuits, but in this review page, parallel circuits divide current. So how is this bank of two resistors going to split the 16.85 milliamps? Well, it turns out that we have the current split into these two values, 3.92 milliamps and 12.93 milliamps. That's how it was split according to your calculations. And here is your conclusion to the thought question. Did the higher ohmic branch, which is 330 ohms, in fact flow the lower current of 3.92 milliamps? Yes, it did. And did the lower ohmic branch, in this case of 100 ohms, being less resistance, allow a greater amount of current flow of 12.93 milliamps? And the answer is yes. Cool. Next step, we will go ahead and do this. So the consideration now, the task is we're going to use Ohm's law, and we're going to calculate the voltage for VR1, VR2, and VR3. In other words, there will be part of the 5 volts divided across R1, and part of that 5 volts is divided across R2 and 3. Series circuits divide, and you'll see this in a moment, but we'll go through the calculations using Ohm's law. Now, how did we use Ohm's law before? If you look at the triangle, and if you're looking for the V part of the triangle, you take your thumb and you put your thumb over the letter V. When you take your thumb and put it over the letter V, what do you see left over in this formula triangle is an I times an R. So the formula for V is written as V equals I times R. And that's what I have here shown on the upper left. VR1, the voltage across R1, is the current of R1 times the ohms of R1. VR2 is the current of R1 times the ohms, excuse me, the current of R2 times the ohms of R2. And finally, the voltage across R3 is the current through R3 times the ohms of R3. And I have that written down with some numerical values here. Your VR1 is in fact equal to 16.85 milliamps times 220. You'll calculate a voltage. VR2 is going to be the current through R2, which is the lower 3.92 milliamps, but multiply by the 330 ohms, you'll get a voltage you will calculate here. Step number 3, the VR3 is the current through R3 times the ohms of R3, and you will get a voltage here. All right. You'll do these calculations on your own. They're pretty straightforward. And write down in your journal what you think these calculated values should be. So at this point in time, you should put the video on pause, do the calculation, and then when you come back, we will do the calculations together and verify that our calculations are in sync with each other. All right? All right. So put that on pause. So you have the benefit of the full screen in front of you that shows all the numbers. I'm going to just show this part here. Step number 1, we want to do a calculation for VR1 that's equal to the IR1 times the ohms of R1. So the 16.85, we'll go ahead and turn the calculator on, 16.85 milli shift M, there's my milli, and I'm going to multiply that by 220, and I will calculate a voltage of 3.71, because I'm going to round that to 3.71. So 3.71 volts is what I calculate. See what you calculate. Hopefully it's the same thing, and we'll find out in a moment whether we're in sync with each other or not. Let's go ahead and do the calculation for VR2. So for VR2, we said that that would be 3.92 milliamps times 330 ohms. So let's go ahead and do that on our calculator. Clear. And we'll go ahead, 3.92 milliamps, milli. Right, there's my milli. And I'm going to multiply this by 330. And I get 1.29 volts. Okay, 1.29 volts. And what you should write down what it is that you calculate. Hopefully it is the same number, and we'll go from here. Next value that we're going to calculate is going to be step number 3. And step number 3, there's some controversy regarding this. You'll see in a moment what that controversy is, and I'll show you how easy it is for us to fix this controversial moment coming up. But we have a voltage across R3 we want to calculate, and that's going to be equal to 12.93 milliamps times 100 ohms. All right, so when we go to do this, let's go ahead and do this. And on our calculator, clear, we will have 12.93 shift here. So 12.93 milli right there. And then I'm going to multiply this by 100 right there. And, oh, okay, no controversy. I get 1.29 volts is what I would write down. And I want you to think about this. Didn't we just calculate a moment ago 1.29 volts by using a different current and different ohms? I'm using 12.93 milliamps times 100 ohms because that's what the step said for us to do for step number 3. For the voltage across R3, it's 12.93 milliamps times 100 ohms right there, and you get 1.29 volts. But we also got that by multiplying 3.92 milliamps times 330 ohms. Let's double check that. So clear the calculator. And we will take 3.92 milli. Well, there's my 3.92 milli. And I'm going to multiply this by 330. So it's a different current, different ohms. I still get 1.29 volts. How is that possible? How is the voltage across R2 calculate to be the same as the voltage across R3? Did we make a mistake somewhere? I want you to think about that. Thought question. Think, think, think. Should they be the same? Should they not be the same? What do you think? Let me stop the share here, or actually go back to share screen. And on the share screen, you can see you now have numbers here, okay? You now have a voltage for R1, R2, and R3. And we just calculated 1.29 from step number 2, and you just calculated 1.29 for step number 3. Should the voltage across R2 be the same as the voltage across R3? The answer is yes. The answer is, of course, because we learned this back in the parallel circuits training video, that the branches of a parallel bank, which is a group of parallel resistances, each branch has the same amount of voltage. Isn't the top of R2 connected to the top of R3? Yes. Isn't the bottom of R2 connected to the bottom of R3? Yes. Lo and behold, they have the same voltage, okay? And so your calculated values are in sync with the theory. And so hopefully we will now just go ahead, pop the numbers in. 3.71, 1.29, 1.29, and that's what it is we calculated a moment ago, and now we're happy campers. The next task, after we determine the individual voltages across the resistances, we are going to look at this topic, and this topic is described as determining the technician test point voltages. And there's a very specific task at hand why we do this. Okay, so before we go to actually delve into the voltages, let's do a review of the concept of electron current flow. We said before, electron current flow is different from conventional current flow, which is the one that was described to us by Benjamin Franklin. The electron current flow describes electrons, which is a subatomic particle, leaving the negative plate of your voltage source. So if you look at item number 1, it says electrons always leave the negative plate of the voltage source to flow through the circuit. Look at my voltage source. V1, 5 volts. Which plate is negative? We said that the longer plate is positive and the shorter plate is negative. And voltage sources are commonly shown with 2 plates, 4 plates, or 6 plates, depending upon who drew the schematic. In our case, we're using a 4-plate DC voltage source. And the shorter plate in this case, being the negative side of the voltage source, it happens to be on the left-hand side, and that's where the electrons emanate from. The electrons will flow out of the voltage source to the left, okay? Through point B, through R1, into point A at the corner. Now, that describes item number 1. So item number 1 says electrons always exit the negative plate of the voltage source. Next will be item number 2. It says the electrons always return to the positive plate of the voltage source after flowing through the circuit. So the electrons, as they flow out of the voltage source, come down to point A, down to point G, flow to the right, and it splits at point F. So part of the current goes up through R2, the rest of it continues and goes up through R3. Remember, there's no current going to ground. This is not an earth ground. This is only a reference point. We'll talk about the reference point later, but the current is forced to go up through R3, up to point D, and at point D, it wraps around, goes to the right. And guess what? This current that flows through R3 combines with the current through R2. They combine together to add up to the total current going back to the voltage source. So item number 2 says the electrons always return to which plate? The positive plate of the voltage source after flowing through the circuit. In other words, the current doesn't just flow from negative to positive within itself, through within the voltage source itself. Item number 3, electrons always enter the negative side of devices. This is important because this helps you mark the polarities of voltages across the device. Yes, you calculated a VR1 of, what did we calculate? VR1 was 1.29 volts, I believe that was. So of 1.29 volts, the VR1, whatever we calculated, I thought it was a little bit more than that. Yeah, it should have been 3.71. Anyway, so as you calculated that voltage, how is that voltage polarized across R1? Remember, voltages are polarized. And when you hook up your voltmeter, you have to be aware of which side of the device the red probe goes and which side of the device the black probe goes. So electrons always enter a device on the negative side of that device. And the electrons, item number 4, always exit the positive side of that device. So if you look at R1, the electrons flow into the right and flow out of the left. So the right-hand side must be the negative side of the resistor, and the left-hand side must be the positive side of that resistor, because that is how the current flows through R1. That is how the current flows out of your voltage source, flows out of the negative plate, and as it comes out, it must go into the negative side of R1, exiting the positive side of R1. And as the current flows down to point A to point G and it flows over to point F, take a look at what happens at point F. The current splits, we said, but as the current flows up through R2, it flows into the bottom lead of R2, which means the bottom lead must be negative. The current flows through R2 and it exits R2 on the top lead. Therefore, the top lead must be positive because that's the exit point of the current electron current through R2. So the bottom of R2 is negative, the top of R2 is positive. And by the same reasoning, the current that flows through R3 makes the bottom of R3 negative and the bottom of the top of R3 positive. And as these currents combine at point C, they will add back up to the total current of 16.85 milliamps to return to the voltage source. So these first 4 points are really important points to remember about electron current flow in and out of your voltage sources, as well as into and out of devices in your circuit. What this allows you to do is item number 5. And item number 5 is very critical for you to do in your journals. You should mark, put in black ink, you should mark the polarities plus and minus, how, of all of the devices in your schematics. Okay? Based on items 1 through 4 above, take a look at how I've marked this. If you look at the simple series circuit, the electrons leave the negative plate, flow down, go over to the right, come up, and as the electrons flow to the left through R1, the electrons flow into the negative side of R1, through R1, and exit the positive side, and then the currents continue to the positive side of the voltage source. So that means now you've got polarity markings across the voltage source based on the plates. Long plate is positive, short plate is negative. So you mark plus on this side, negative on this side. You also have the polarity markings across R1. The right side of R1 is negative, the left side of R1 is positive because the current flows, in this case, into the negative side and out of the positive side. You also should now mark the polarities across R2 and R3. Marking the polarities, the electrons flow into the bottom of both of these resistors, which makes the bottom lead of both of these resistors negative, flows through each of the resistors, and as the current leaves these resistors at the top lead, it must leave the positive side of these devices. So that means that the positive side of R2 and 3 are on the top side. So these polarity markings are critical for you to understand what to do in your next step. Next step is pretty easy, but the polarity markings help you understand how to go into the next step, which is here. And the next step says the task. You want to write the voltage values, VR1, VR2, VR3, that you previously calculated onto your schematic. Now, this may necessitate you redrawing your schematic. Well, fortunately, you've got a lot of fresh pages in your journal, and make this big. Don't make this tiny. Make this schematic on your journal probably full page, okay? Probably would be nice to uh, occupy the entire left margin all the way to the right margin of your journal with this size schematic. And what you should be marking on your schematic are the resistors as we have originally planned. You should mark the letter points A, B, C, D across the top, E, F, G on the bottom. You should mark, instead of writing 220 ohms, we already know the ohms. The most important part of the task coming up, it's not the ohms. The most important part coming up are the voltages. We need to see the voltage across R1 as being 3.71 volts, and we also need to see the polarity of the voltages, negative on the right, positive on the left, by virtue of the previous slide. We need to see the polarities across the voltage source. We need to see the voltage value of R2, 1.29 volts, as equal to the voltage across R3. They're both 1.29 because voltage across parallel branches is the same. And we must see the polarity markings on either side of R2 and R3. So this is a very important schematic. Probably would behoove you to put a pause in your video at this moment and copy this into your journal. And you can see how critically important this will be to your next step. So you take a moment to pause and then come back. And when you come back, we will see the next page. All right, my friends, this is our next page. And the task here is to determine something we call technician test point voltages. So what are technician test point voltages? What's the purpose of this? Technician test point voltages, first of all, is a safe, fast, one hand on the red probe for testing, while the black probe is clipped to ground, freeing the other hand. Fast because you're only handling one probe. Safe because as you're handling only one probe, the other hand is in your pocket, or the other hand is holding onto your digital multimeter. So the likelihood of you getting a shock that goes from your left hand to your right hand, crossing your heart, stopping your heart potentially with enough current, is minimized unless you're standing in water. All right. So this is a really handy, safe, fast, one-handed test method where we can take the black probe, and we will use either a mini hook or we will use an alligator clip and clip it to a common reference point. And we call that common reference point here ground. So as the black lead is connected to ground in each one of these values we're looking for, then we're only using the red probe to touch point A. We're only using the red probe to switch to point B, the red probe to switch to C, D, E, and F, and G. Very fast testing once you have these values of voltages either calculated or given to you, and in most cases, as a field tech, these values of voltages on a test panel will be given to you by your supervisor or in the trade manual for the test panel that you're testing. And you will go about doing your testing as a technician, pretty much identical to what the photograph shows. You don't see the left hand holding anything but the digital multimeter. In fact, you see a little bit of the thumb on the lower left edge of the multimeter, but the black probe is not in your left hand at all. The black probe is simply clipped to a ground point, a reference point, and we're only using one hand, one probe, to tap each point of interest on the test panel. And the reference for this particular photo is given to us by this reference right here. So I did put the reference below the image. I did not take this picture. All right, so that being said, let's evaluate and see how we can calculate what these test point voltages are, because we have these points in our previous schematic and in the upcoming schematic. So let's go ahead into the next illustration. Here we go. All right. So you have a task, and the task is to determine a test point voltage called VA, subscript A. And the way you read this, is voltage at point A with respect to ground. Voltage at point A with respect to ground. In fact, that is so important. I think I'm going to need to add that in here. So I'm going to pause this. All right, so, oops, I need to do a share, silly me. Let me go ahead and put this on pause. Okay, so as we're back to our screen for technician test point voltage, V subscript A, and you do read this as shown in yellow, read as the voltage at point A, and then in quotes, with respect to ground. Now, I mentioned that in the previous training, that phrase will come up. Electrically, the same as one phrase, and with respect to ground is the other phrase. And if you don't have with respect to ground written in your journals, please do so at this point in time. Make sure that you have that phrase in quotation marks, as we will be using it for a good number of slides forthcoming. So we read this capital V with a subscript A, voltage at point A with respect to ground. So as we've said before, technician test point voltages are fast and they're safe. Why? Because it's a one-handed method of making measurements instead of two hands. So your likelihood of getting shocked is reduced dramatically. So what do you do with the black probe? The black probe is clipped to ground. And in this case, you can see my black arrow on the lower right. I have a black arrow indicating I've got the black probe and I'm no hand on it. I'm just going to clip it one time with either an alligator or a hook to the bottom of R3. As long as I have it clipped to the bottom of my R3 and my circuit is built correctly, life is good. All I need is one hand on my red probe to do these point measurements, and it's going to be very fast. So let's analyze and see if we can determine what that value is before we go through the measurements. It's really simple. If you read the definition, it says V subscript A, voltage at point A, is equal to the sum. Okay, sum means we're going to add. What are we going to sum? We're going to add we're going to add something called loop voltages. And I'll define and show you what loop voltages are in a moment. But we're going to add loop voltages how? Algebraically. Oh God. Oh no, that phrase algebra. No, don't let it freak you out. All we're going to be accounting for is positive versus negative. Okay. So you're adding voltages algebraically from point A to ground. Black probe is at ground. Take a look at the red arrow. Red arrow is at point A. So I can show you this. We have two different pathways, or several different pathways to go to ground from point A. So one way, I have a short CCW, and CCW stands for what? Counterclockwise. So look at an analog clock, not your digital Apple Watch or Samsung, whatever, Android watch, nothing digital. Look at the traditional analog clock. And which way do the hands spin? The hands spin clockwise. Counterclockwise means we're spinning in a reverse direction. So one method is taking a look at a short counterclockwise path. And what is that path? And I have that path written here as points A, G, F, and E. Well, here's A. So the path will go from A to G, G to F, and F to E. If we take this counterclockwise path from A to G, how many volts exist between A and G? None. It's just a bare wire. So we have a 0. And then how about between G and F at the bottom? Are they connected? Yes. Is there any device there other than wire? No. So we're going to add another 0. And then how about the last move between point F to point E, which is ground. Are they connected? Yes. Is there a device that drops voltage like a resistor or LED? No. So we add another zero. So on the short path, counterclockwise path, going from points A to G, F to E, I have a 0 volt plus 0 volt plus 0 volts. Guess what? Point A should measure 0 volts. Now there's more than one path between A and E. It doesn't matter which path we take. If we do our summing algebraically correctly, whichever path we take between A to ground should add to be the same value. So here's another concept. The short path points A, G, F, and E are said to be electrically the same. I said we'd come back to that phrase. Why are A, G, F, and E electrically the same? Why are they equal to ground? Why is A equal to 0 volts? Well, take a look at point A. Is point A connected to G? Yes. Is G connected to F? Yes. Is F connected to E? Yes. They are all connected, and the only thing that connects them together is wire. No LEDs, no resistors. So if you have points that are physically connected by wire, then those points are said to be electrically the same. So we will have 0 volts at point A looking at that path. There's one more path, long path. We'll go clockwise this time and take a look at the path that I've indicated here, starting at points A. So you're going to go from A to B, B to C, C to D, D finally to E. So as we move from point A to point B, because that's the first move going clockwise, the first polarity we encounter is what? Positive. So we have a positive, how much voltage? 3.71 volts. Now we're on the other side of R1. So now we go from point B to point C. Here's point B, here's point C. What exists between point B and C? A voltage source. So as we move from point B to the right towards point C, what's the first polarity we encounter? The first polarity we encounter is negative. Negative how much voltage here? 5. That's why in the formula, we show it as subtract 5. So we have a positive 3.71, subtract 5. Then we're at point C. Now at point C, we're going to go from C to D, and we happen to have 0 volts between C to D because there's only a wire. There's a 0 there. Then you're at point D. We got one more leg to go to point E. So from point D down to point E, the very first polarity we encounter is positive. Positive how much? 1.29 volts. So algebraically, look at what we have on the long path. We have a positive 3.71 volts, subtract 5, add 0, add 1.29 volts. Does that in fact add to 0? Yes, it does. So here as a last statement, either path should always algebraically add to the same voltage, which in this case is 0 for point A. Okay. You'll see these concepts repeated in the next couple of points of interest, and the figuring things out will be a lot easier as we look at point B, point C, point D. So here is point B. We read this as the voltage at point B with respect to ground. So where's my red probe? My red probe is now at point B. Black probe stays at ground. So this is one hand. I'm going to switch from A to B. My loop voltages from B to ground, one path, the short clockwise path, starts at B to C to D to E. So from B to C, what do I encounter first? Is a negative 5 volts. Now I show that here is minus 5, negative 5. From point C to D, I have 0 volts. From D to E, I have a positive 1.29 volts. So if I do the math, negative 5 volts plus 0 plus 1.29, I get a negative 3.71 volts. Write that down. Long path, counterclockwise. I'm going to start at B and now go backwards in the circuit. I'm going to go B to the left to A, down to G, over to F, and finally to E. So if I go leftways from point B, the very first polarity I'm going to encounter is what? Negative how much? 3.71 volts. So I have write down negative 3.71 volts. Now I'm going to add what's left. Between A and G is a 0. Between G and F is a 0. And between F and E is a 0. So check this out. Negative 3.71 plus 0 plus 0 plus 0. It's going to be negative 3.71 volts. That's how you figure this out. And whichever path we took, did my last statement hold true that either path should always algebraically add to be the same value? And in this case, the first shorter path was negative 3.71 volts, and the longer path also negative 3.71 volts. Moving on to point C. Now the red probe changes. The red probe is now, it was at A, was at B, now is at point C. And again, you're only doing one hand. The black probe is attached with a clip alligator to point E. So what do we have here? The short path, clockwise. I'm simply going to go from C to D to E. Is that what I've written down here? The short clockwise path is C to D to E. Between C and D, I have 0. Between D and E, I have a positive 1.29. So my short path, I get a positive 1.29 volts. Is there another way between these 2 points that's also short? Yeah, I have this written down as a short counterclockwise path going from C, F to E. So here's C, here's F, here's E. So from C going downwards, I encounter a positive what? 1.29. And then I'm going to add a 0 between F and E. So positive 1.29 plus a 0. Hey, guess what? On this path, I also get 1.29 volts. All right, now let's play with the long path. The long counterclockwise path in this case takes us from C to B, B to A to G, to F to E. So the long way around, let's see what we encounter. The very first thing we encounter as we move with a red probe leftwards, we encounter a polarity of positive 5 volts. Okay, positive is what the red probe sees first. Now we're at point B. At point B, we're going to go from B to A, and we encounter what polarity first? A negative. First we encounter positive 5, and then we see a negative 3.71 volts. Mathematically, we do it this way. 5 minus 3.71, and then add what's left. Well, what's left on this wire between A and G is a 0. What's left on this bottom wire between G and F is a 0. What's left between F and E is also a 0. So if you look at the math, 5 subtract 3.71 plus 0, 0, 0, I end up with 1.29 volts. Wow, isn't that wonderful? They algebraically add to the same voltage. So that's what you should write down for voltage at point C with respect to ground. Let's take a look at the next one. D, voltage at point D with respect to ground. The short way is go from D with your red probe downwards, and as you go downwards, you encounter a positive what? 1.29 volts. It is flat out positive 1.29 volts. If you go the long way around, D to C, C to B to A to G, F and E, you can see the math, it's there. It's going to add up to be 1.29 volts positive. And yes, either path, we end up with the same value. So you now have the voltage at point D. How about at E? E is very interesting. E, the voltage at point E with respect to ground, well, hey, guess what? Point E is ground. So if I put the red probe at E and the black probe at E, there's no difference of potential because both probes are connected to the same point. Remember, voltage is defined 3 ways. Voltage is defined as the pressure to move electricity. Voltage is also defined as the push to move electricity, EMF. Voltage is also defined as the difference of charge between 2 points. Well, we're measuring the same point, so there is no difference. So it's got to be a zero. If you want to prove this to yourself, then let's use the long path. And the long path is to take E going counterclockwise all the way around this loop. And if you do this all the way around the loop, you will encounter and see these numbers: negative 1.29 plus 0 plus 5 minus 3.71 plus 0, 0, 0. Guess what, my friends? We end up with a 0. So you've proved to yourself point E is ground. Red probe at point E, red probe at ground is going to be a 0. And you've proved mathematically by using the loop method, algebraically adding, we will get 0. So it proves the voltage at point E is in fact ground, is in fact 0. Next, voltage at point F. Red probe is now at F. Well, guess what, my friends? Between F and E, they are electrically the same point. We used that phrase before, electrically the same. F and E are connected with a wire with no resistor, no LED between them. 0 ohms is the ideal ohm for resistance for a wire. So if you have points that are connected with 0 ohm wires, they are electrically the same. So if E is a 0, then F for sure must be 0 volts. And if you follow the long path, you'll algebraically find that it is also 0. So F and E, F is the same as ground because they're connected. And by the same token, if we look at the last point of interest, point G, same logic here. G, F, and E are all three electrically the same. In fact, A, G, F, and E are all electrically the same. Is A connected to G, connected to F, connected to E? And is there any resistor or LED between them? Only thing is a wire. Therefore, A, G, F, and E are electrically the same. Okay? That means if I have ground at point E, 0 volts at point E, I have 0 volts at point F, 0 volts at point G, and we started with 0 volts at point A. Neato. So this is how you noodle out on any schematic, is by using the technician test point method for voltages. Black lead hooks up to a ground reference point wherever that might be, and I chose to not attach the ground to the voltage source, which is typically what textbooks do. This is a little more stretch of your brain cells here, which is good. And then we're going to determine what each of the voltages are at specific points with respect to ground. All right. So with all this being said, what is the task in front of us? The task in front of us, here we go, is to fill in this page of calculations. Now, we've just done this, okay? You've done this along the way, and hopefully if you've been taking notes along the way and doing your calculations along the way, then you should have this filled in pretty quickly because the values are already in your journal. And if you haven't transferred them onto your journal, then you should take a moment, pause the video, do so now. And then in a moment, we will check your calculations to the solutions. So put it on pause. Make sure you have these values written in your journal. And when we come back, we'll check your numbers. Well, welcome back. Here's all the numbers. Cool. I won't read them back to you, but you've done this already. R equivalent, R total, I total, I total. I total is split into two branches. We have a smaller current in the higher ohmic branch. We have a larger current in the lower ohmic branch. We use Ohm's law to determine the voltages across each of the resistors. 3.71 volts was across R1, and then R2 and R3 have the same voltage because they are parallel devices. And then we also just finished the technician voltages of these values to ground. All right, so what we're going to do is now go to our board and confirm all of these values that we've written down. Okay, amigos, here we go. So hopefully you've taken the time to carefully build your circuit in a fashion that is similar to this. It doesn't have to be identical, but it should be similar. You don't have to use the same points as I have, but electrically, you should have things hooked up so that they do jive with your schematic. So we have the voltage source at the rails, and the voltage source at the rails does present the negative side to point B of the R1 resistor. R1 comes across to point A, down to point G, over to point F and E. Ground is this point here, point E, and there's several attachment points for ground. I can use this resistor leg as ground. I can hook up a jumper here. I can hook up to this jumper, this jumper. Any one of these areas is ground. I can also hook up to F. F is also ground. G is also ground because they're all connected together, as is this jumper here. Ground is actually on this side of R1 as well, because isn't point A electrically the same as G, F, and E? So I have a number of places I can hook up the black hook for measuring the voltages when we get there. But let's go ahead and review the circuit build. So my voltage source comes from my red and blue rail. So the positive side comes over to the top of point C. Point C is attached to the top of point D. These are the top of the R2 and R3 resistors. The bottom of R2 and 3 resistors are connected via a bunch of jumper wires, ultimately to this yellow jumper wire here. That's where the bottom of these two resistors are connected together. And then from here, this makes a connection back to this side of R1, and then ultimately to the negative rail right here. So I have these staggered. This resistor makes a connection, R2 makes a connection to the common wire between E and F, and allows me a point to make a break for measuring current. And the same thing over here, I can pull this out for I can make a separate current measurement that's separate of what's going on here. Now, that being said, I also have my points labeled. This is positive, this is negative. Point A is here, point B is here, C is here, D is here, E, F, and G. So this jives with the schematic that you were presented. So that being said, the very first thing we need to do, which we did earlier, but I'm going to reiterate because it's pretty fast, is to confirm our total ohms and our equivalent ohms. So we're going to, in order for us to do this, as I've said, you have to remove the power supply so that the circuitry of the power supply is not goofing us up. And then I'm going to scoosh this over just a bit and raise this up just a scoosh. Okay, so that being said there, let's go ahead and do the continuity test again and touch the two probes together. Make sure this goes to 0 ohms. That LED lights up, and if the microphone is nice, it might pick up a beep. And beep, trust me, the beep. Then we go to ohms, and on omega, we want to confirm we have total ohms. That's close to the 296.74 ohms. So I'm going to touch here and here. And 296.74 is what we're looking for. I end up with, let me light this up so we can see this better. Since this does illuminate nicely, go ahead and make the measurement. And I'm hoping for something close to 296 and change. I get 297 and change. Pretty good. Now, we wanted to confirm that the individual you wouldn't get the R total matching unless the individual resistors were correct and that the individual resistors were in the right places. Now, I said that we were able to measure the value of the equivalent resistance by removing this jumper for a moment. That isolates the bank from the series resistor. So if I go to hook up here to here, I should get the 76.74. Something pretty close to it, 77.4. Yes, hook up over here to here. Touch, touch, touch right there, touch. There's my 77. Touch over here. If I just go across one, it measures both. If I go across this one, it measures the both of them together, 77.4. So it doesn't matter which way I cross between the corners of this parallel bank, here to here, I'm still going to get the in the case of my board, 77.4. All right, so that's great. So that takes care of the R measurements. Now let's go ahead and confirm the, oops, didn't mean to pull this guy, put this guy back. I meant to put this jumper back. Okay, jumper back. And just to make sure the circuit was rebuilt correctly, since I yanked a couple things out, let's just double check total ohms again. Do I get my 297 and change? Yes, I do. All right, circuit's built properly. So that confirms your resistance total and your equivalent resistance. The next thing to fill in the chart is your total current. So in order for us to do total current, we need to do two things. We need to bring the power supply back. We need to energize the power supply, and we also need to determine where we want to measure total current. So total current can be measured a number of places on my board. I seldom want to go to the rail. Yes, I could pull this brown jumper and measure total current here, but like I say, I seldom want to go anywhere near the rail. So I'll measure total current somewhere else in the circuit. And total current is really best measured anywhere in near a series resistor. So R1 is my series resistor. R1 is connected between point A to point B, and I have a convenient jumper right here. So if I pull this jumper out, I will create an open between here and here, and that open is where I will hook up my ammeter. So what I'm going to do is hook up the power supply and plug in my USB to the power supply. Pardon my hand for a moment, sorry. Go to here, hello, all right, that's good there. And I'm going to remove this jumper that I said would be for measuring current. Okay, and then I'm going to energize the power supply. Okay, that's energized, it's ready to go. I now want to switch this from ohms, from continuity over to measuring current. So measuring current, and then my red and black probes can't go, I recommend you not go anywhere near the rails. I recommend you connect this only to where the circuit has been opened, and the circuit was opened, and I will use a pen to do this, because last time I used a probe to do this, I blew my fuse. So that's one part of the open right there that was previously connected through a jumper to point G. So my open is here and here. Which side of the open is more positive, which side of the open is more negative determines which color probe goes where. And if you noodle this out correctly, the negative side of the circuit is connected to point A. So this should be where my black probe goes, and my red rail connects through all of this, all of this, all of this to point G. So this should be where my red probe goes. So if I hook this up, am I going to get something close to my total current of 16.85 milliamps? Let's go ahead and see. Current, milliamps, DC, red probe goes here, black probe goes here. And I was hoping to see something that was 16.45. I get 17.45. That's okay. Again, our resistors are not exact. Our board has some ohms in it, as do the wires. But is this reasonably close? The answer is yes. And does this read positive or negative? It reads positive, 17.47. If I go to reverse the leads, like so, I'm going to see a negative 17.47. Doesn't mean we have negative current. It just means that my probes are reading the polarity that is presented on the board. And for me to have this read properly, the red probe must be on the positive side of the open, black probe on the negative side of the open, 17.46 milliamps in this case. All right. So in order for me to measure the branch currents, which I'm going to do in just a moment, I have to rebuild the circuit right there. That's rebuilt. And the branch current I'm going to measure right now is IR2. I'm going to measure the current that goes through R2, and I've got a convenient jumper right here that I can pull out. Gently yank that out, set it aside. I've now created an open. And again, I don't use my probe as a pointer. This is one part of my open, and this is the other part of the open. This resistor was previously connected to point F. It is no longer connected to point F. The resistor is on row 20, point F is on row 21. So there's a definite open here between the resistor and point F. Which side is more positive? the side that's hooked up to the positive rail. So that means this leg of the resistor is more positive. Point F is hooked up to the negative side of the circuit. So my black probe should go here. Now let's go ahead and hook this up. Red probe to here, black probe to here, and we should see, because this is the higher ohms, the lower of the two currents. I think it was 3 something. Let's see. Yeah, I had 3.92 milliamps, and we have 4.07, which, hey, all right. Again, we're pretty close. Now, if I want to measure the current of the second branch of the parallel, I do have to rebuild that first branch. So I'm going to take this, rebuild this over here so that's intact. And now just remove the jumper here. Set that aside. And now I've created an open. And again, I'm not going to use my probes as pointers, but point E is here, the bottom of the resistor, and it was previously hooked up to this end of the yellow jumper. The resistor's on row 15, the jumper's on row 14. They are not connected. I do have it open, and the more positive side is the resistor, more negative side is this jumper, and I expect to see something close to my calculated 12.93 milliamps, and slightly higher. That's okay, because as I've said, I don't have these resistors as being exact. There's a tolerance involved, but this is reasonably close to the 12.93. It's 13 milliamps. So we're happy with how things are flowing right now. So that takes care of our current measurements. Now the most fun part will be the test point voltages, and this will go very, very quickly. So I'm going to set this up. And so for me to set this up, I'm going to pause this for just a moment. Just a moment. Hello. All right, so this part here is the fastest part of our measurements, and this is why technicians prefer to use this method. We've already determined the voltage at point A to ground, B to ground, C to ground with these values. So A to ground was a 0, B to ground was a negative 371. The next two, C and D, are positive 1.29 volts, and then zeros for the other points of interest. So let's see how our actual measurements work out. Now, if you notice, I've got a little mini hook that's attached to point E. Point E is my ground. One hand is here, the other hand is holding this probe. So this is the one-handed method. I'm not likely to get shocked this way as long as I'm not standing in a puddle of water. So let's take a look at point A. So let's go ahead, change this. Very important you change this. If you leave this on milliamp, you may blow a fuse. So change this to volts, DC, the display reads volts, light this up, and according to our previous calculations, it should be something near 0. So here's A. 0. And then point B is right here. We expect something close to a negative 371. Let's see what happens. Ooh, look at that. We have a negative, not 371, but again, fairly close. I get a negative 38. All right. And then at point C and point D, I get a positive 129. Well, here's C. I get 134.1 compared to my 129. I'm pretty happy camper at this point. Go to point D. Again, 1.34. Happy with that as well. So C and D are equal to each other, and they are a positive something close to my 1.29. Now, E, F, and G, we said were equivalent to each other or identical to each other because they were all ground electrically the same point. So it should have a 0, 0, 0 for E, F, and G. So here's E, touching the same point. That's a 0. Go to F. That's a 0. That's like a thousandth of a volt. And the reason why it's not exactly 0, hey, these wires could be acting like antennae. And as antenna, they're picking up all kinds of radio frequencies, and sometimes stray radio frequencies may show up as some number like this. Now let's go to G, should be close to 0, if not 0. And again, it's a little stray radio frequency noise being picked up by the wire because the wire acts like an antenna. That's pretty much a 0. So my E was 0 or close to 0. F is 0 or close to 0, and G is close to 0. And does that jive with our values here? See how fast that was. So again, A, 0. B, negative 3.71 is my negative 3.8. C, positive 1.34. D, positive 1.34. E, in this case, effectively 0. F, effectively 0. G, effectively 0. See how fast that was? That's called your technician point voltage testing method. Really, really love it in the field because it is so fast. All right, next. All right, so we are back to our page, and let's go to the next one here with all the values filled in. There's all the values filled in. These are the values of our calculations, and our measurements were pretty close. You should, as a matter of consistency and a good matter of practice, write down your calculated values also. That way you don't have to, at some point in time in the future, oh, I know it was close, but how close was it? So as you're making your measurements along the way, be nice to have those values written next to, maybe with a different color ink in your journal, but would be nice to have those next to your calculated values that you've written down. All right, what's next? There's more. Watch this. You think you know what you ought to know about series parallel circuits and technician voltages? Well, you got more coming at you. And again, if you like this approach of looking at schematics, looking at circuit builds, looking at the theory concepts, and then doing the calculations and then doing the measurements hands-on like we're doing, if you like this approach, give the YouTube a thumbs up, subscribe, please. And if you want to support the channel even more, then you sign on as a Patreon, and it allows me to be able to have the time and resources to be able to make more of these if you find this at all helpful to you. All right, here we go. Next. Ta-da! All right, this is a question. This is a challenge series parallel question. And the task is for you to determine the following values of technician multi-point voltages, okay? Multi-test point voltages, not single voltages from one point to ground, from another point to ground, not with respect to ground, but you may from time to time be asked to actually use two different probes and connect the two different probes to two different points. And can we reconcile what these values ought to be before we go to make the measurements? Pretty simple to do. So take a look at the suggestion, what to be mindful of. It says for you to be mindful of what? Polarities of the voltages between the red to the black probe. I highlighted that in yellow. From the red to the black probe. All right. So the very first multi-test point voltage you're going to consider is VCA. CA is point C, point A in subscript. So that means you're going to measure the voltage from point C with respect to A. Did you hear? Not with respect to ground, but with respect to the second alpha letter that's shown. So red probe goes to the first alpha letter, C. The black probe goes to the second letter, which is A. And so red probe to point C, black probe to point A. What do you think you're going to calculate between C and A? Well, we've done enough of these, and hopefully you have a comfort level with this, but take a look at this carefully. What it is we have here is the red probe is at C, black probe is at A. The way you reconcile this very simply is you take the red probe and you drag it visually. You can use a red pen on the schematics that you've drawn. You can use a red pen as a pointer and go from C to the left towards point A. What do you see along the way? The first thing you see is a positive what? 5 volts. The next thing you encounter takes you from C to B. Now you have one more leg from B to A. What do you encounter? The first thing you encounter is a negative side of R1. Negative how much? 3.71 volts. Wow. 5 positive and a negative 371. You do the math. 5 subtract 371, 3.71. What do you get? Point C, you get a number. Do the calculation. 5 subtract 3.71. What do you get? Hopefully you get 1.29 volts. Then hopefully it's positive. Okay. And we'll confirm that in a moment. So write that value down for a calculation. Take a look at the next one. The next one is the voltage at point B. Let me just go to the next one. Here we go. The next one is F to B. Did I put... Oops, didn't mean to do that. Sorry, gave it away. Okay, F to B. So that means red probe at F, black probe at B. So I put the red probe at F, black probe at B. So what do I have between the two? So B is here, red is here, and that means we are going to have, as you move from the red probe from F to C, C over to B, first thing you encounter is going to be a negative 1.29, and then you encounter a positive 5. So negative 1.29, positive 5. Looks like we're going to get something that may be a positive 3.71. Negative 1.29 plus 5. How about the last one, G to D? If the red probe were at G and the black probe were at D, let's just go this way. From G to F is a 0. F to E is a 0. From E going up to D, first thing we encounter is a negative. Negative what? Negative 1.29. That's what it is you'd expect to see with the red probe on G, black probe on D. You have these values written down. Let's see how they jive with our calculations. Here's our calculations. Yep. From C to A was positive 5, subtract 3.71. We had a positive 1.29 volts. From F to B, so F to B, so here's F, we encounter a negative 1.29, sorry. Add 5 gives me a positive 3.71 volts. And lastly, from point G to point D, the short way, the 0 plus a 0, and then we encounter a negative 1.29 volts before we hit point D. There's my negative 1.29 volts. Let's see how this compares with our measurements coming up. All right. So with our measurements coming up, let me go ahead and do this. Okay, so the first one we're going to confirm is the C to A. So red probe goes on C, black probe goes on A, as shown in this illustration. We anticipate we should get a positive 1.29 volts. Let's go ahead and see if that works out to be the case. We will go to the camera. Okay, so red probe is on C. Circuit's on, energized, connected. All the jumpers are back in place. Red probe is on C. Black probe is going to be on A. So we anticipate it should be a positive 1.29. Let's see what happens. Okay, as I said, close enough for government work. All right. That's very, very good. All right. The next value of voltage that we're going to confirm will be this. All right, so the next value we're going to reconcile here is the voltage between points F and B. Again, the first letter, F, gets the red probe. The second letter is what gets the black probe, which is what's shown in the schematic. Red probe is at F, black probe is at B. What do we see between these two probes? The first thing you encounter from the red probe moving up should be a negative 1.29. And then from point C over to point B, moving leftwards, we have a positive 5 volts. So that should reconcile to be 3.71 volts positive between F and B. Let's see what it looks like on our breadboard. So F to B. So here is F. This is F. All of this is F. Bottom of the resistor is F. And then B will be here on the left side of R1. We're hoping to see something close to 3.71. And there we go. 3.822, because my power supply is a little beefier than 5 volts. Nice. So that confirms your voltage F to B. One more to go. Okay, so with one more to go, let me just go ahead and do it this way. Hit share here and hit share. Oop. All right. And the last one to go is this one here. Oops, come back here. Went too far. Oh no, this is right. All right, so we want volt between G and D. So again, first letter gets the red probe, second letter gets the black probe. Red probe goes to G and black probe goes to D. And if we look at the short path on the bottom, from G to F is a 0, F to E is a 0. And then when we're going up from E up to point D, we encounter a negative 1.29. So that's what we reconciled earlier. Let's see how this measures out. So let's go ahead and stop the share. And as I stop the share, black probe is going to be at D. Right there is D. Okay. Now I can use this one here as D. That way it won't get in the way of my lettering. I'll just do it this way. And point G, which is here. We expect to see something close to a negative 1.29 because my power supply is more than 5. This will probably be a little bit more than negative 129. And yes, it's negative 1.344. And the negative sign is prominently shown on the left-hand side of my digital multimeter. Pretty good, my friends. So we've learned a bunch of things in this particular video training session. The technician voltage test point is critical for you to understand, evaluate, and do the measurements of. And then the multi-test point voltages, such as what we've shown in the past 3 steps with these 3 different sets of measuring points, is also very important for you to understand as a technician. All right, that's great. So now that takes us to this here. And we will finish with this guy here. All right, that completes our topic number 8 training video, troubleshooting for series parallel circuits. This is a part A. Not done with series parallel. There's a whole lot more to learn about series parallel troubleshooting. We've gone over a number of concepts, principles, reviewed series circuit concepts, parallel circuit concepts, how we combine them, how we do current analysis. We did current divider. We did Ohm's law. And then we had a number of new things for you to do some thinking on, some calculating on, and some measuring on. So again, if you like this approach of the schematics shown, some questions, theory that's presented to you, the method of how we do the analysis via calculations, and then verify those calculations by using actual circuit builds and measurements, please do hit the like button, hit the subscribe button. It helps me make more videos. And if you like also, you can hit Patreon and really support this channel for being able to build more videos. So with that, my friends, I thank you so much for your kind attention. Hopefully this has been a good learning experience for you. It's certainly a fun experience for me, sharing this with you all. And I look forward to seeing you on the next series parallel troubleshooting Part B coming up. Adios.